Welcome back. This is sections 5.5 and 5.6. We're combining them because they both have to do with properties of parallelograms. Using this parallelogram, we're going to make some conjectures about the parallelogram. And in fact, these really aren't conjectures because some of them we've already either proven or we can conclude based on things that we already know. So we have the parallelogram, and the first thing that we're being asked about are consecutive angles and what their relationships are. So consecutive angles, of course, would be, for example, angles 1 and 2 are consecutive. Angles 2 and 3 are consecutive. Angles 3 and 4 are consecutive. And angles 4 and 1 are consecutive, right? They're next to each other, so to speak. So what can we conclude about these consecutive angles? Well, since this is a parallelogram, we know that these two sides are parallel. We could consider this side a transversal intersecting those parallel lines, and these two angles would be co-interior angles. And we know that co-interior angles with parallel lines are supplementary. Now, we also could apply it to the different set of consecutive angles. We know that these two sides are parallel. We could say that this is a transversal intersecting those parallel lines. So these co-interior angles are also supplementary. So instead of thinking of it as parallel lines, let's just think of it as a parallelogram. So we now know that consecutive angles are supplementary. And of course, just a reminder that supplementary angles are angles that add up to 180 degrees. All right, next one, opposite sides. Opposite sides of a parallelogram. Well, we actually have already proven that opposite sides of a parallelogram are congruent, right? And we proved this as a homework problem, and I believe it was number 5 on page 240. You could go back and check that out. There was the proof there. So we know that the opposite sides of a parallelogram are congruent. All right, well, how about opposite angles of a parallelogram? So for example, opposite angles, angle 1 and angle 2 would be opposite. Angle 3 and angle 4 would be opposite. So opposite angles are across from each other. Well, let's think about this. Opposite angles. It looks like, just by looking at those angles, that opposite angles should be congruent. But how do we know? How do we know that they are congruent? Well, what if I drew in a diagonal here? No, that's not the best diagonal. Let's do that again. There we go. That's a little bit better. And created two triangles, triangle 1 and triangle 2. Well, notice we already have some congruent sides because we know opposite sides of a parallelogram are congruent. And this diagonal would be congruent to itself. So we could prove that these two triangles are congruent by side, side, side. Therefore, by CPCTC, their angles are congruent. So that means that this angle would be congruent to this angle. And of course, we could draw our diagonal the other way, starting from here and going this way, and same thinking, this is congruent to itself, so this angle is congruent to this angle by CPCTC. So what have we concluded? We've concluded that opposite angles in a parallelogram are indeed congruent. And finally, they ask us about the diagonals of a parallelogram. All right, so let's draw in our two diagonals. So there's one, and there's the other one. And it's a little bit hard to tell here, and I'm not so sure we're going to go through any reasoning to conclude this, but I'm just going to go ahead and tell you that these two diagonals bisect one another. So that's congruent to that, and that is congruent to that. Right? Diagonals in a parallelogram bisect each other. All right, good. So there's some properties of parallelograms that maybe we didn't know before this. So let's connect this to physics with some definitions here. These are going to be some important definitions. You'll want to write them in your notebook. Vector, a quantity that has magnitude and direction. Resultant vector, or vector sum, is a single vector that has the same effect as two vectors. And then the connection to parallelograms is that the resultant vector is the diagonal of the parallelogram. So write these down in your notebook, and now let's see on the next slide how we apply this to math and to physics. All right, so here we have a diagram. It's obviously an airplane, right? And we have some vectors. So vectors have both magnitude and direction, and they're often represented by a ray. So you can see some rays here. If I trace this ray, trace this ray, trace this ray, right? There's three rays there. Now let's explain what each of these rays is as vectors. So we'll start up here. It says vector v sub e represents engine velocity. So when you're flying in a plane, there are actually two forces that impact the direction of the airplane. One of those forces is the force produced by the engines. Well, this plane in our diagram, its engines are forcing it along this vector, right? In that direction with that magnitude, right? Pretty strong engines, pretty strong magnitude. Now let's go down here. Vector v sub w represents wind velocity. Okay, so we're flying along in a plane, and there's also wind currents up in the air. And those wind currents could be pushing the plane left or right. Well, in this case, the wind is coming from the left and pushing the plane in this direction with this magnitude. Now notice that the vector for the wind is much shorter than the vector for the engines. That's because the engines are producing a much greater force. So its vector is much longer, right? That's how we identified the magnitude of a vector, is by the length of the ray. Now, what they've done is, with these dotted lines, they have created a parallelogram, right? And the red vector inside of that parallelogram, as it says right here, is the resultant vector of the vector produced by the engines and the vector produced by the wind, right? And that resultant vector is the actual speed and direction of the plane, right? So we started with two vectors with different directions and different magnitudes, and the resultant vector, which ends up being the diagonal of the parallelogram, is the resultant vector, which gives us the actual speed and direction of the plane. All right, we're going to finish this video lesson with some other conjectures, and I'm just going to give you these conjectures. All right, but they're things that you want to write down and remember. So we're going to start with rhombus. The rhombus diagonals conjecture says that the diagonals of a rhombus are perpendicular to one another. So let's go ahead and label some things here. We're going to label those as being perpendicular to one another. Diagonals of a rhombus also bisect each other. Well, this makes sense. A rhombus is a parallelogram, and we saw it previously in the video that the diagonals of a parallelogram bisect one another. So we can mark it as such. Next, the rhombus angle conjecture says that the diagonals of a rhombus bisect the angles. So we could go through here. That's congruent to that. That's congruent to that. That's congruent to that. and this one's going to be a little hard, 2, 3, 4, and 1, 2, 3, 4. There we go. So we are showing that those diagonals are bisecting each angle. All right, let's move on to the rectangle. So the rectangle diagonals conjecture says that the diagonals are congruent, right? So if we have A, B, C, D, we know that AC is congruent to BD. The conjecture also states that the diagonals bisect each other. And this should make sense to us because a rectangle is also a parallelogram. And so therefore, that is congruent to that, and that is congruent to that. And then finally, let's move on to the square. Now, a square is a rhombus and a rectangle, and of course a parallelogram. So we're going to take all the characteristics from a rhombus and a rectangle, and we're going to put them together, right? And that's why the square diagonals conjecture says the diagonals are congruent, the diagonals are perpendicular, the diagonals bisect the angles, and the diagonals bisect each other.